Everything is related to everything else, but near things are more related than distant ones. This is the first law of geography, coined by famous geographer Waldo Tobler in the late 1970s. And as trivial as it might sound, the first law of geography applies to countless spatial phenomena. Take elevation, for example, the height above sea level.
Elevation tends to change gradually with distance. At two close-by locations, the elevation is likely very similar. Now increase the distance between two locations, and the elevation is much more likely to differ.
Or take noise, for example. It is relatively quiet here, and it will still be relatively quiet close by. But increase the distance.
Doors closing.
The first law of geography is both a blessing and a curse. It is a curse because it makes statistical analysis difficult or sometimes even impossible. A common assumption for most statistical tests is statistical independence. When observations are independent, it does not really matter which sample we happen to pick to study a phenomenon, say the height of a population. Pick any large enough number of individuals and you will get similar estimates for the average height in the population. Now here's the problem with the first law of geography. The first law of geography leads to spatial autocorrelation when neighboring individuals are similar. And this violates the assumption of statistical independence. So, if our sample includes only neighbors, our estimate might be biased. Depending on where we pick the individuals, we might underestimate or overestimate the average height in the population. There is another problem. We would like to know how good our estimates are. How well does the average height of the sample reflect that of the population? If, in a sufficiently large sample, the height varies much across individuals, our estimate of the population parameter is rather weak. Instead, if the height is similar across individuals, we can be rather confident that the estimate is good. However, in the presence of spatial autocorrelation, this confidence is entirely misplaced. The individuals in the sample are similar and the variance is low. But this is because the samples are not independent. They are autocorrelated. Spatial autocorrelation wrongly suggests that the uncertainty of the phenomenon is small. Taken together, in the presence of spatial autocorrelation, we likely make biased and wrong conclusions. At the same time, we are very confident that the conclusions are right. Estimating the average height of a population is not a serious problem. Unfortunately, spatial autocorrelation also affects problems that matter. We might come to entirely wrong conclusions and be very certain about them, all because of neglecting the first law of geography. On the other hand, the first law of geography is a blessing because it makes spatial interpolation possible. In the next video, we will see what spatial interpolation is and how we can compute spatial interpolation. On y va!